Hi, so welcome to the next lecture on digital signal processing, which is a part of MLSP course, Machine Learning for Signal Processing course. In today's lecture, we're going to discuss about periodic signals. So in the last lecture, we saw signals, but now we're looking at periodic signals. So what are periodic signals? So they repeat in time. Our time is discrete, notation n, and you can see this signal on the left hand side. This has a repeating structure, and it repeats after how many instants? I can see it can repeat after 10 instances. So which means the time period of this signal is 10. Similarly, the signal on the right hand side also has a time period of 10 because it repeats itself after every 10 time steps. So these are periodic signals. Now, what is the fundamental frequency? F naught. All of you know F naught is 1 upon T naught. T naught is the time period. So the question is, how do we find the fundamental frequency? To find the fundamental frequency, if I'm given a signal xn, how do I find its fundamental frequency? So one very popular or very common way is to find autocorrelation. You remember in the previous video we had seen correlation. Correlation means, so correlation is used to find similarity of two signals. So, but in this case, we are trying to find the similarity of xn with itself. That is why it is called autocorrelation. So not cross correlation, but autocorrelation. So what do? We just shift xn and multiply with itself element wise and then add it up. So if we do that, we get yn. Now you can see, okay, so first, what is the time period of xn? In this case, the time period of xn is 16, right? Because after every, so you see whatever is the value at 0, the same value occurs at 16, and then subsequently all the values are repeated. Now the time period of xn is 16. If I do an autocorrelation, you see what is y0? Y is the autocorrelation. Y0 is maximum, right? Because xn is multiplying with xn element wise and added up. So that is the maximum correlation, which means it has a very large value. Now if I shift my xn, so one copy of xn, if I shift towards right, and as I am shifting, you can see my autocorrelation y is going down and down and down, and it increases and goes down, and it attains a peak exactly at 16. So at 16, it again shoots up, again peaks. Why? Because now the first cell, or if you say xn has got two cycles, the first cycle exactly overlaps with the second cycle. That is why you get a high correlation. So that is the way, that is one way, very popular way of extracting fundamental frequency of a signal, of a periodic signal. Why is it called fundamental frequency? Because this is the most this is basically repeating, the signal is repeating at this frequency. Of course, if you do a Fourier analysis, if you see, there are other frequencies also present, which we will see in the subsequent slides. Okay, so now this is an important thing which I was going to mention, that you have got a signal xn on the left hand side. This signal can be seen as a sum of sinusoids. So this signal, which has a time period of 16, the left hand side xn, the leftmost, the time period is 16. It can be seen as a combination of many other periodic signals, with basically sinusoidal signals. So I can decompose it, and what I find is this is a sum of one sinusoid of time period 16 and another sinusoid of time period 8. So why time period 8? Because, you know, if time period is 8, then it will repeat, then it will also repeat after every 16 time instants, because simply because 8 is a multiple of 16, or 16 is a multiple of 8. 8 is a 16 upon 2. So this means I am decomposing my signal into two sinusoids in this case. Similarly, I can decompose into many sinusoids. So okay, let's look at a periodic signal, a very popular periodic signal, simply a sinusoid. What is a sinusoid? My xn is equal to some amplitude x naught times sine of 2 pi f naught n plus phi naught. F naught is the fundamental frequency and phi naught is the phase. It's a very well behaved continuous differentiable signal, sinusoid signal. That is why it can serve as an orthogonal basis. We'll see what does that mean. Okay, so any periodic signal can be decomposed into sum of sinusoids, weighted sum of sinusoids. So for example, if I have my xn, it can be seen, if xn is a periodic signal, then it can be seen as, let's say the time period is capital N. Then my xn can be seen as xk sine 2 pi f k n plus phi k, where k goes from 0 to capital N. So this is where fk is k upon capital N. Okay, so let's come to the definition of Fourier transforms. All of you have read Fourier transforms earlier, but this is a refresher. Okay, so the Fourier transform, the reference book which I am looking here is Oppenheim, very popular book. But anyways, the concept which we are interested in is very simple. Xt is a periodic signal and it is continuous in time. So this periodic continuous signal can be written as a weighted sum of sinusoids. So e to the power j k omega naught t is a sinusoid with the fundamental frequency omega naught, and k is the harmonic. When k is 0, then it is a DC signal or a constant signal. But when k is 1, it is a sinusoid with frequency omega naught. When k is 2, sinusoid with frequency 2 omega naught. K is 3, sinusoid with frequency 3 omega naught. So like that. So why I'm using exponential? Because it's easy to do mathematical manipulation with the exponential. So sinusoid is, it's the imaginary part of exponential of j k omega naught t. Now, so Fourier transform is, okay, I want to express xt as a weighted sum of these sinusoids, and these weights are called the coefficients, the Fourier coefficients, and these xk are discrete and they are not periodic. They are discrete and not periodic. And you can do a very simple analysis. If you multiply xt with exponential of minus j k omega naught t, and you integrate over entire xt, which is basically one period of xt, then what you get is xk. It's a very simple multiplication and followed by the integration. So very easily you can derive the coefficients xk. And similarly the reverse way also. If you want to go from xk to xt, then the formula is given on the top. So now what happens if my xt is not periodic? If xt is not periodic, then my x of j omega also becomes not periodic, but it is continuous. Then x of j omega becomes continuous, which means earlier we needed only a finite number of coefficients to represent xt, but now we need infinite number of coefficients because x j omega is continuous. Okay, so this was a very short refresher of Fourier transforms, but now I'm going to give an overview at how Fourier transforms are working. Let us imagine the first case when xt is a continuous and aperiodic signal. Then my x omega will also be continuous and aperiodic. Now if I make my xt periodic, right, with a period t naught, so xt is continuous and periodic, what happens to my x omega? It becomes discrete and it stays aperiodic. So basically, I don't need infinite number of coefficients, I only need a finite number of coefficients. And this number is given by 1 upon t naught, 2 upon t naught, so on up to t naught. Okay, so then what happens if my xt is also discrete? Then it is discrete and periodic. Now my xk will also be discrete, but it will also become periodic. So sampling in one domain causes periodicity in the other domain. You see, in the second case, sampling in the xk domain or x omega domain causes periodicity in the xt domain, and in this following third case, sampling in the time domain causes periodicity in the frequency domain or xk domain. Now, what happens if my xn is discrete and aperiodic? Then my x omega is continuous but periodic. Now you see, sampling in the, consider the first case and the fourth case. We are just sampling xt of the first case. The result is my x omega of the first case becomes periodic, means the copies appear at the at regular frequency. So this is what happens. Sampling in one domain causes periodicity in the other domain. And this is a very simple chart that if my one domain is continuous, the other domain will be aperiodic. If my one domain is discrete, the other domain will be periodic. Okay, anyway, so this was just an overview of Fourier transform. But what we need in this course is discrete Fourier transform. This is very important for us. We will not require continuous time Fourier series or anything like that. We will be interested in discrete Fourier transform. What is discrete Fourier transform? So my xn is a discrete signal, and it is also periodic signal. It's discrete and periodic. Now this periodicity is assumed. What does that mean? It means I only take a finite window of xn. In this case, the window length is capital N. I take a finite window of xn, and I assume that this window is repeating periodically, right? So if I want to find x capital N plus 1, that is same as x 1, right? Because it is periodic, it will be repeating. Similarly, now if I do a Fourier transform, my xk, this is also discrete and periodic. Why it is discrete? Because my xn is periodic, so xk is discrete. Now why it is periodic? Because my xn is discrete, therefore it is periodic, right? Periodicity in one domain causes discreteness in the other domain, and discreteness in one domain causes periodicity in the other domain. Okay, so now my xn is also discrete and periodic, xk is also discrete and periodic, and both have length of capital N. Right? So this means I'm only interested in the window of length capital N, and outside this window will be just a repetition of the same values. So basically I use a modulo function to bring back my indices to the range 0 to capital N minus 1. Okay, so this is discrete Fourier transform. This will be the most useful transform in this course. And reference is the book by Quartieri, Thomas Quartieri, and chapter number 2. But I think if you understand this concept, you are pretty much there. Now coming to one property of discrete Fourier transform. If my xn is real, which is there in this course, mostly you will see real xn. But anyways, if my xn is real, then it is seen that the xk follows this property. X of minus k is x star k. X is complex, right? So x star means complex conjugate. So this means if x of minus k is x star of k, this means my mod of xk is an even function, right? Because mod of x of minus k is equal to mod of xk, because x star mod is same as x mod. So which means my xk which means x of minus k is x of k mod. So xk is an even function, but the angle of xk is an odd function. Why? Because angle of x star will be negative of the angle of x. So that is why angle of xk is an odd function. Now, okay, I have explained this point, but I'm writing it here. Periodicity implies that x of k, you are only concerned with the modulo value, because you are concerned with only the window of 0 to n minus 1. So because of periodicity, this property becomes x of minus k modulo n is x star of k modulo n. Okay, now a small derivation. Can I derive this property? Actually, all these properties can be derived from the basic equation which you have learned. So you have learned xk is xn e to the power minus j 2 pi k by capital N and summation over all small n. This is my xk. Now I want to derive this property. What is x of minus k? Is it equal to x star of k? Okay, take x star k, no problem. And what you get is I just take a star on both the sides. So xn becomes x star of n, and exponential of minus j becomes exponential of plus j. Now you see x star of n will be same as xn. Why? Because xn is real. This is given. Xn is real, so x star of n is same as xn. Now I want to convert it into a form of xk. So take an minus sign and then take another minus sign. So replace k with minus k and add a minus sign in the front. Nothing changes, but what changes is now the right hand side is x of minus k, right? They compare the form with the first equation and you get this is equal to x of minus k. That's it, a very simple derivation. Okay, now coming to discrete Fourier transform. Let's look at some more properties of DFT which are very useful for us. The most important properties, can I find out what is the periodicity of a signal? Let us say xn is a signal given to me. Originally this signal is sinusoidal of 2 pi 2.32 times n. So what is the periodicity? The periodicity is basically 2 pi 1 upon 16 times n. So the time period is 16, right? 2 upon 32 is 16. So 2 pi. So the general form is 2 pi by capital T times n, and where capital T is the time period. So in this case, the time period is 16. But how do if I don't know this form equation, I'm given the signal. How do I find the Fourier transform? How do I find the periodicity? So very simple ways. I find the Fourier transform and I see where is the peak in the Fourier transform. The peak in the Fourier transform tells me about the periodic property. Okay, so let's look at the Fourier transform. What do you get here? You get peaks. You get two peaks, in fact. One peak is at 0, 1, 2 at k equal to 2. Another peak is at k equal to how much? 30. So 31. Okay, so what happens is where will the peak be in modulo in mod xk? So the peak will be at, so see xn. What is my xn? It is sine 2 pi. So I will convert it into the complex form, e to the power j 2 pi 2.32 n. I know this is xn is the imaginary part of this, so no problem. So now you compute xk simply from the equation. You know xn e to the power minus j 2 pi k upon capital N times n. That is my xk. Now where will the peak occur? So if capital N is 32, now if my capital N is, I am choosing capital N. Capital N is I am choosing because this is the capital N is the NFFT, the Fourier transform property. So if my capital N is 32, then a large magnitude will appear whenever the exponentials cancel each other, right? Whenever my e to the power minus j 2 pi k upon capital N times small n, when multiplied with xn, which is e to the power j 2 pi 32 n, when these two cancel out, right? Because when one is the complex conjugate of the other and they cancel out, then you get sum over 1, right? Which is a very large value. So large magnitude of xk will appear whenever the exponentials cancel each other. So that is why you get k equal to 2. When k is 2, then my xn will match exactly with the e to the minus j 2 pi k upon capital N. So that is why they will cancel out each other, and we will get the peak in mod xk. Okay, I think this part is clear. Okay, now the question is, where does the other peak appear? It's very simple. You just take the modulo. You know that, okay, you know this is a, as we saw in the previous slide, that for real signal, my discrete Fourier transform is, the magnitude is an even function. So this means if peak is at xk, peak will also be there at, peak is there at mod of xk, then peak will also be there at mod of x of minus k, which means my peak is appearing at k equal to minus 2 also. Now what is minus 2? I take a modulo 32 because capital N is 32. So modulo 32 is, it will be 32 minus 2, which will be 30, right? Okay, so let's go to the next example. In this example, we have xn is sum of two frequencies, one sinusoid with the time period of 32 upon 2, which means 16, other sinusoid time period of 32 upon 8, which means 4. So there are two frequencies present. Now, how do I find out what frequencies are present? Just take the DFT. If I take the DFT, discrete Fourier transform, in the magnitude plot, I get two peaks. You can see one is at 2, another one is at k equal to 8. So I can do the same analysis what I did before. Where will the peak be in mod xk? And the same analysis will hold that whenever the exponentials, their complex conjugate, they cancel out each other, then you will get a peak. Same analysis you do, and you find they will cancel out when it's e to the power minus j 2 pi k upon capital N times small n. If my capital N is 32, then at k equal to 2 and at k equal to 8, they will cancel out. For k equal to 2, first one will cancel out and you'll get a large magnitude. At k equal to 8, second one will cancel out and you get a large magnitude. And similarly, the right hand images are obtained because of the mirror symmetry. So at k equal to minus 2 and k equal to minus 8, so you compute the right half. Now, okay, now I can do zero padding. What does that mean? Let us say I have a signal which is finite, let's say it's 32 length, but I want to get a more resolution. If I take my NFFT equal to 16, so what do I get? My signal xn was length 32, but if I do an NFFT only of length 16, so what does that mean? It means that I am first of all not using the other 16 values, and the magnitude DFT I get is like this in the first figure. Now if I increase my NFFT to 32, which means my signal also is of length 32, my NFFT also 32, then I get this kind of a signal. But if I increase my NFFT to, let's say, 128 or to 64 or 128, then I get a sharper resolution. I get more resolution of the DFT, right? But how do I attain an NFFT of 64? So I have to do a padding, which means I have to assume that xn after 32 is followed by all zeros. So with this padding, I can compute an NFFT of a DFT with NFFT of 64, which means I can get more resolution. You can see it's a high resolution plot. Okay, now how do I achieve DFT, or how do I perform DFT in Python? NumPy has an implementation of FFT. It's called FFT fast Fourier transform, which is an algorithm for implementing discrete Fourier transform. It's called fast Fourier transform because it's very, very fast. The computational complexity is very small as compared to ordinary DFT. It's just an implementation thing. That's why it's called FFT. But in principle, it is same as DFT. Okay, so this is the documentation you can go through and you can use it in Python. Now, okay, so this was about uh, discrete Fourier transforms of periodic signals. Now, why do we need spectral representation? Why do we need a spectrum? Why do we need the Fourier transform? So Fourier transform is called spectrum because it tells you what energy is present at what frequencies, or what frequencies are strongly, dominatingly present, and what frequencies are not so much present. So this is called spectral analysis or spectral representation. So why is it useful? It is useful for, as we saw, analysis of periodicity of a signal. The peaks in the spectrum will tell you what frequencies are dominant. Then this representation is very compact. It is very compact. You can if you know that only certain frequencies are present, you can discard other frequencies which are not very strong, and you can just keep the strong frequencies, and you can send this information or compress the signal with that information. Then it disentangles sinusoid frequencies. It disentangles our signal, even if the signal looks very messy, but if it has got periodicity, then my spectral representation kind of disentangles and shows me what frequencies are prominently present. And it becomes very useful to find out what signals are mixed. I'll give you an example. For example, in your electric signal, if in your any kind of signal, audio signal anywhere, you get a noise of 50 hertz, and you can immediately tell this is because of some electrical interference, because in India the power supply is at 50 hertz. So there is some magnetic resonance or some interference because of power supply, which is affecting your signal. And how do you find that out? Simply by spectral analysis. You do a spectral analysis and you find out, okay, 50 hertz frequency is present. So this happened once with me. There was a lot of noise in the audio transmission in the convocation of IIT Kanpur, and we were looking at why there is so much of noise, and I did a Fourier analysis and I found out that this frequency is occurring exactly at 50 hertz. So immediately the concerned people, they recognized that there was an electrical source nearby which is causing all this interference, and then they were able to repair that fault, and audio transmission again became clean. Okay, so what did we study in this lecture today? We studied about periodicity, and we studied about Fourier transforms to represent periodic signals. These are some of the references which you can go through. So thank you very much.